So, good morning or good evening, depending on where we are. It's 10 o'clock right now. So I think the first talk is it the Han?
Yes, yeah, it is.
Am I pronouncing that correctly?
Yeah, that's perfectly right. Thank you.
Perfect. Are you ready to take it away?
Yes, I think I don't have the option. Okay, share is here. Okay, I can share the screen.
Perfect.
Okay.
Yep, looks beautiful.
Okay, can you see the slide clearly, please?
Yep, all good.
All right. Okay. Hi, everybody. I'm Thiang Han from Tisa University. I'm going to talk about a regulation dilemma in AI development. This is joint work with Lenaerts, Moniz, Pereira, and Francisco Santos. In our works, we try to model the AI development competitions among actors like developers, big tech companies, or even governments who try to develop and deploy certain technologies ahead of others, to gain benefits. And we will use taking from evolutionary game theory in order to understand the dynamics of these competitions, and from there we try to devise suitable regulations in order to drive this competition in a beneficial outcome for the society. And here in this talk, I'm going to try to convince that here there's not just safety behavior dilemma where collectively safety is desirable by the society, but we cannot get it because unsafe behavior can gain advantage and evolve. And we just don't have this safety dilemma. We also have a regulation dilemma here, because it is much more tricky to regulate safety behavior, unsafe behaviors, while avoiding stifling any beneficial innovations. Okay, so just a bit of motivations. Recently, we have seen significant progress in AI research and development. We have seen lots of successful deployments and developments of new AI technologies, as well as like applying technologies in new application domains such as self-driving car, autonomous weapons, etc. And because of the great benefits promised by these advanced AI technologies, especially for those who are ahead of others in the competitions, there has been significant concerns from researchers and political leaders that there is a potential arms race amongst actors in these competitions, which eventually could lead to cutting corners on safety requirements, ethical requirements, and we can end up with unsafe and unethical AI products, which can lead to very severe consequences, losing public trust, or we could even have some kind of existential problems. So because of the importance of these problems, it's important to think about and to try to come up with suitable regulations so that we can ensure beneficial outcomes for all, while avoiding kind of preventing suitable or beneficial innovations. We want to have safety behavior, we want ethical behavior, but on the other hand, we don't want to stifling unnecessarily any kind of beneficial innovations that we can gain from advanced technologies. And we have seen lots of efforts in AI regulation and governance. For example, the recent EU AI regulation framework. So in order to do that, to devise suitable regulations and governance, a number of questions need answering. For example, what do we actually know about the dynamics of this AI race? What do we know about the impacts of regulatory actions on such race dynamics? And is regulations always useful, and useful in what sense? Here we can think about issues like over-regulations. Yeah? If we over-regulate, for example, a certain technology is not too risky, why it can give us significant benefits. If we regulate it too much, we could prevent the society to get the most benefit from such a technology. So one way, one approach to answer all these questions is, of course, to collect data about behavior patterns. Let's say, okay, how companies, how governments, how developers behave when they are faced with this kind of competitions. But the problem is, at the early stage of development or deployment, we usually don't have sufficient data to make suitable or good predictions about the behaviors or the impacts of any regulatory actions. So yeah, so what can we do? Because of the lack of data, an usual approach, a scientific approach, is to build mathematical models, for example. Yeah, so we can try to come up with mathematical models, and over time, once we have more data, we can improve the models. But of course, all models are wrong. But hopefully, with our modeling, we can provide some suitable insights that can be used to think in advance to devise, to prevent any potential issues that could be associated with advanced technologies. So that is our approach. We will use methods from evolutionary game theory and agent-based modeling to study these competitions and to understand what kind of regulatory actions, for example, certain form of incentive that can be used to drive this competition into a beneficial outcome. So here is our first effort, very recently published in Journal of AI Research, where we try to answer the first questions. What do we actually know about the dynamics of this alleged AI race? I put alleged here because, of course, there's still much debate about whether there's an actual arms race in a certain domain. Yeah. I'm going to present a simplified model of this dynamics for illustrations. We have many more kind of variations of the model and analysis in the paper, which if you are interested, you can look at. But the model should be sufficient to give you a taste of what we are doing. So assuming here that we have a domain X, be it self-driving car or autonomous weapon robotics, and we have a number of actors, companies, developers who try to reach the supremacy in the domain X. And in order to reach the supremacy in this domain, there's a number of advancements that they need to achieve in order to reach the supremacy in that domain. So here we denote that as W advancements. And with each advancement, the actors can gain intermediate benefits by deploying their developed technologies, even if it's not the supremacy one, but they already can gain intermediate benefits from deploying their technologies. And here you can see that if you're familiar with game theory, evolutionary game theory, it can be nicely captured using the framework of repeated games, which we are going to use here. So here, for each advancement or round of the repeated game, players need to make a choice. They can either play safe, meaning that they fully comply with any safety requirements, or they can play unsafe, meaning that they ignore safety precautions completely. Of course, we can think about a more continuous model where we could say players comply with a certain degree, for example. Here, the safe option is not only costly, but it also takes more time than unsafe. So you have playing safe means that players have to pay a cost C, while if playing unsafe, players do not have to pay any cost. And also the safe player moves with a speed S equal 1, while unsafe player can move faster with a speed larger than 1. This is a very important parameter in a model, which we will analyze carefully later. Okay, here we made a few simplifying assumptions for the ease of analysis. So each advancement requires the same time, and each advancement generates exactly the same benefit B. So in order to analyze these models, we first need to derive the payoffs first in one round, then we derive the payoff for the whole repeated games. Here, we can see that if the first player plays safe, and the second player also plays safe, both players pay a cost while sharing the intermediate benefit of the round. While if a safe player faces an unsafe player, the safe one has to pay a cost while getting a smaller benefit than the one who play unsafe. Yeah, so here you can clearly see that playing unsafe is advantageous. While when two unsafe players plays, they share the benefit without paying the cost. We have extended this to multiplayer games. You can look at the paper for that. So now we can define what can be the potential strategies in this AI race, these AI competitions. So we can think about unconditional behaviors, which is usually considered in the literature of repeated games. That is a good starting point when we model the situations. So here we have AS saying always safe, meaning that this player would always comply with safety compliance in all the round of the competitions. Or we have unconditional unsafe player who always play unsafe, and yeah, and we also can have any combinations. Yeah? They can play safe in one round and unsafe in the other round. The thing here is that whenever there's unsafe activities involved, there's a risk of disaster. So because there's some chance that we get an unsafe product at the end, which can lead to some disaster that are not anticipated. And here we model risk of disaster as follows. We assume that the risk of disaster is proportional to the number of unsafe activities in the development process. And here P risk denotes the probability that disaster strikes when safety precaution is completely ignored. We consider both the situations where this disaster only impacts the focal player who do unsafe behaviors, or they also can be shared amongst different players in the interactions. So here we can also have a collective risk problem. But in the context of AI race, people argue that the impact is more individualized. However, we show that even when it is collective risk, the results is quite robust. So here we can now derive the average gains. It is important because it represents the fitness or social success in this evolutionary dynamics methods. Yeah. So what you need to focus here is, for example, here whenever we have AU or the unsafe behaviors, here just an example, we also derive payoff for the combinations or the conditional safe behaviors in the paper. So for example, here, whenever you have unsafe activities, there's a probability that the player would lose everything they have gained during their development because of disaster. Yeah. Why for safe player, there's no such a risk, but of course they gain much less because they lose the competitions against the AU. So here we use evolutionary game theory to analyze this model. Here is the standard way. Yeah, so let's assume that we have a populations of different types of strategies. For example, here we have AS and AU players, and at time t says a player is randomly selected from the populations for behavior updates, which the player can either freely explore another behavior or otherwise it can imitate another randomly selected player from the populations. And the idea is that the probability of updating the behavior is so the more successful the co-player is, the more likely I will adopt his or her strategies in my next interactions. So using this evolutionary game theory method, we can analyze the model and answer the following questions. So we can answer what behavior dominates in the evolutionary dynamics and what parameter influence the dominance. Here we can get both analytical and numerical results, as you have seen here. We show the frequency of AU in a population of AS and AU. We also have the model where we have other conditional strategies. Yeah. So we show what is the frequency of unsafe behavior in the populations as a function of the speed of development. Here it is the speed when safety is completely ignored and the probability that AI disaster strikes when safety precaution is completely ignored. So here we can derive these conditions. Yeah? So the yellow line here, characterized by this inequality, we show that below this yellow line, unsafe behavior is preferred by natural selections. And below this white line, populations of AU of unsafe behavior is more beneficial than the populations of AS, meaning that social welfare generated by unsafe behavior is larger than that for AS, because here the risk is low, while the gain from taking risks is much higher. So here, based on these conditions, which also well aligned with numerical results, we can split the behavior space into three different zones. So we have the zone 1 is a compliance zone, and zone 3 is the innovation zone. Here, for these two zones, we don't need any regulations because we already have the behavior that is designed collectively. Yeah. So here we want to have risk-taking behavior, unsafe behavior, and it is selected by natural selections. And in the compliance zone, we want players to play safe, and this is actually selected by natural selections. The issue here is that we have in this zone 2, the dilemma zone, here we want to have safety behavior because it's most beneficial for the society, but it is not selected by evolution. So clearly, we need to regulate unsafe behavior in this dilemma zone. We also can see that from the calculations of social welfare. Yeah, so in the dilemma zone, the social welfare is the lowest. So we have also studied bigger groups. We have shown that the zone 3, the no innovation zone, is the same when we have a larger competitions, larger group competitions. But when the group size increase, the dilemma zone size increase, while the compliance zones decrease. So it implies that for larger competitions, there's more job to do. It's more likely that we need to regulate unsafe behavior here. Okay, so we have seen, so where is it necessary to regulate? So we can have safety dilemma in these AI competitions, but it's very important. It's quite different from other social dilemmas, like the prisoner dilemma, public goods game. Here, we do not always have a dilemma. It depends on the risks of the technologies. In many cases, if we, for example, in zone 1 and zone 3, if we regulate unsafe behavior, it might lead to detrimental effect. So we can see that it is much more complex to deal with than the standard kind of corporations or social dilemmas we usually see in the literature. Okay, so the next part of the talk is that I'm going to talk a bit about how the effect of incentives for the regulations of these AI safety competitions. So here we are going to look at different forms of incentives. We are going to look at peer and institutional incentives, both positive or negative. So for peer punishment, it is defined as players who sacrifice their own speed of development to try to reduce the speed of an unsafe opponent. Yeah, so here PS is the peer punisher. Yeah, so here you can see when PS play with an unsafe player, in the first round, it moves as usual, while then PS see that, okay, AU is doing something unsafe, then I'm going to punish that guy. So both players' speed are reduced. So yeah. So we also can think of institutional punishment, where we have an institution which is not part of the system, and the institution try to reduce the speed of the unsafe behaviors, unsafe players. We also can think about positive incentives in the forms of reward of safe behaviors. Yeah, so for example, here we have RS, which is the rewarder, who whenever seeing that someone doing safe behavior, they can sacrifice their speed and trying to help the co-player to speed up. So now let's look at the results of what is the impact of this incentive for the 3 important zones we have seen previously. So the first one, the most important one, the dilemma zone, because we need to regulate unsafe behavior here. Previously, as you can see that in zone 2, it is completely red, meaning that we always have unsafe behavior. Now with both reward and punishment. By the way, here we plot the unsafe behavior as functions of the cost of providing incentive and the effect of the recipients of the incentive. Yeah. So here we can see that both peer reward and peer punishment lead to improvement in terms of reducing unsafe behavior in the dilemma zone. And reward and punishment is most of the time more efficient than reward, just in slightly worse in a small area in this white triangle. While in the compliance zone, nothing wrong here, because we want to have safety behavior and both type of incentive do not affect that desirable outcome, so everything is fine. Why in the innovation zone, reward is fine because we want to have innovations, so we want to be red here. But in case of punishment, we see over-regulations because here there's whenever the cost of providing incentive is low enough, why there's a great impact on the incentive recipient, then we see much less innovations. So this is undesirable. So let's see how it goes with institutional incentives. Both tie would lead to the same results because here we have some kind of symmetric payoff.
Can I just interrupt here, please? You've got 1 minute left of your talk.
All right, yeah, I'm going to finish within 1 minute.
Perfect, thank you.
Okay, so here with institutional incentives, we can see that it's similar to peer incentive, where we have we can reduce the unsafe behavior in the zone 2, but we also have over-regulations in zone 3. Okay, to sum up, so here we have described a plausible model that can be useful when thinking about the governance of AI technologies. It is a very first attempt, and we are going to develop further on that. But we already can see very interesting behaviors. So we have seen that all incentives can improve safety outcome in the dilemma zones, which is desirable. So we have seen that peer punishment and both types of institutional incentive might lead to over-regulations of beneficial innovations. Why we have peer reward is the only options without any side effect, but usually much less efficient. So we can see here that we have a regulation dilemma here because the most the one without any side effect can lead to something that which is much less efficient than the types of incentives. Okay, so you can look at the papers. I'm not going to talk about future directions. You can have a quick look here. So last but not least, I just want to thank our funders of this research, the Future of Life Institute. Okay, that's all. Thank you very much for your attentions.
Fantastic. Thank you so much. That was a very interesting talk. I think, unfortunately, we don't have enough time for any talky questions. But what I'll do is, if anyone listening does have a question for Thian, I'll keep him as a participant for the time being, and you can type in the Q&A section, and then Thian will be able to see it and reply that way.
Okay.
And then, of course, you could also get in touch via Slack as well.